Hello, good afternoon, everyone. Could you please press the thumbs up sign if you can hear me and you can see the slide? Right, thank you very much. So welcome everyone to the second webinar of the IMath webinar series for this semester. So I would first like to remind everyone that this webinar is being recorded and it is being streamed live on YouTube, and the link will be available on our Institute of Mathematics Facebook page. Okay? So again, welcome. I am Gino Angelo Velasco, the coordinator for research of the Institute of Mathematics. Okay, so for today's webinar, we'll be hearing from Mr. Dom Vito A. Briones. So he will be speaking for the group's Geometry and Representations academic group of the Institute. Mr. Briones is a PhD student, the Institute working under the supervision of Professor Jose Maria Balmaceda. Okay. So this will also serve as his graduate colloquium, which is a requirement in the PhD. So the title of his work is Association Schemes on Triples. So let us all welcome Mr. Don Vito Briones.
Thank you for the introduction, Dr. Velasco. May I share my screen?
Yes, please.
Okay, great, thanks. All right. Hello, can you hear me well enough? Hello?
Yes, Dom, we can hear you.
Okay, great. I will begin. All right.
Yes, please.
Okay, so in this presentation, we'll talk about some of the work my advisor and I are doing for my dissertation. It's about some parameters of a generalization of classical association schemes called association schemes on triples, or ASTs. Specifically, we look at ASTs that arise from two transitive group actions, exploring the relationship between the AST and the acting group. As a concrete example, we'll work mainly with the affine semilinear groups. We start with a brief history of classical association schemes and the motivation to study them and their generalizations. We then talk about classical association schemes as a jumping off point for ASTs. We then look at ASTs, how they arise from two transitive groups, and how their parameters are related to the group action. Finally, we work out some parameters of the ASTs obtained from the affine semilinear groups, providing examples and explicit computations to showcase the methodology of the dissertation. In this section, we introduce classical association schemes and how they're situated in mathematics. They're fundamental in algebraic combinatorics, intersecting numerous fields and unifying seemingly different concepts into a common structure. They allow different areas of math to be amenable through the study of what is, in essence, a single object. Classical association schemes originated from the work of Bose and Shimamoto for designing statistical experiments. Since then, it's become fundamental in the study of a variety of different mathematical areas involving symmetry. Such examples include discrete geom, graphs, directed graphs, coding theory and designs, certain types of algebras, and generalizations of groups and their representations. We take special notice of the relationship between classical association schemes and transitive groups, because it's in this vein that we look at some analogous properties for association schemes on triples and two transitive groups. We'll now provide the necessary theoretical background for today's talk. We will define a classical association scheme as a set of relations with certain symmetry properties. We work with concrete examples along the way, taking particular emphasis on certain parameters called the intersection numbers. These intersection numbers turn out to determine the multiplication in a certain algebra. The terms and results we use are mostly from the classic text Algebraic Combinatorics 1 by Banay and Ito. Okay, So this is our example of an association scheme in its relation form. First, the Ri partition the Cartesian product. Second, given any member xy of R3, the number of W such that replacing y with W yields a member of R1 and replacing x with W yields a member of R2 is independent of the chosen member of R3. For example, if we take 0, 3 in R3, the only W such that 0W is in R1 and W3 is in R2 is W equal to 1. Similarly, if we take 1, 0 in R3, only 2 serves as an intermediate of 1, 0 with respect to R1 and R2. Our third observation is that switching the coordinates of R1 yields R3. And finally, the first relation is the diagonal or the identity relation. These observations are better seen through a graph, as we shall see in the next slide. So here's the graph form of our example, where the relations give the edges of graphs. The first of these, corresponding to the identity, is the graph of loops. Combining these graphs yields the complete directed graph with loops. As for combinatorially interpreting the intersection number P123 is equal to 1, it says that if we take a black edge, the number of ways we can go from the initial point to the terminal point by first going through a red edge and then a blue edge is 1. For example, let's take the black edge 1, 0. The number of ways we can go from 1 to 0 by first going through a red edge and then a blue edge is 1, which is given by this path. So similarly, the only way we can get from 0 to 3 by first going through a red edge and then a blue edge is 1, which is this and then this. We take this opportunity to highlight a special case of intersection number called the valency, which gives us the outflow of a certain color. For example, the valency K1 is the number of red edges coming out of any given vertex. We see that the value of K1 in this example is equal to 1. Here's the formal definition of a classical association scheme in terms of relations. It's a partition of the Cartesian product, which has the identity relation, is closed under transposition, and where a certain symmetry or regularity condition is satisfied. The symmetry condition says that if we take an xy in Rk, the number of W such that xw is in Ri and wy is in Rj depends only on I, j, and k. As the Pijk counts the W that serve as intersection points of edges xw and Ri and wy and Rj, the Pijk are also called the intersection numbers, the special cases of which the outflows are called the valencies. There's a way to view association schemes where the intersection numbers and valencies have a more algebraic role. If we take the adjacency matrices, AI of the graphs prior, their products can be expressed as linear combinations amongst themselves. In other words, the linear span is closed under multiplication, and so is both a vector space and a ring, or in other words, an algebra called the adjacency algebra. In fact, the coefficients of the product of the ith and jth adjacency matrices, when we express them in terms of the basis AK, are precisely the intersection numbers Pijk. In particular, this tells us that the multiplication in the algebra is determined by the Pijk. For example, we can check commutativity in the algebra simply by looking at the intersection numbers. As a less superficial application, of which there are many, the valencies, particular intersection numbers, give an algebra homomorphism from the adjacency algebra to the complex numbers. As an example, here's the matrix form of our association scheme from earlier. Notice that the product A1, A2 is equal to A3, which is in the span of the adjacency matrices. Looking at the subscripts of the left-hand side of the equation, and then looking at the coefficients of the basis elements on the right-hand side, we obtain P120, P121, and P122 are all 0, while P123 is equal to 1. All right, now in this section, we'll transition from classical association schemes to association schemes on triples. We view ASTs as ternary relations, working through a concrete example and emphasizing the relevance and interpretations of the analogs of the intersection numbers. Our discussion is based mostly upon the work of Mestre and Bhattacharya, entitled Association Schemes on Triples and a Ternary Algebra. This is our example of an AST in its relation form. The relations are now ternary, or subsets of the triple Cartesian product. We make some analogous observations. First, they partition the triple Cartesian product. Second, we have an analog of valency, a sort of outflow given a distinct pair. For example, given the ordered pair 1, 2, only 1, 2, 3 is in R4. Similarly, given 2, 3, only 2, 3, 1 is in R4. Indeed, any distinct pair has an outflow of 1 with respect to R4. This common outflow is denoted N43. The subscript indicates the relation. The superscript tells us that we are looking at the outflow with respect to the third coordinate. The third observation mimics the symmetry condition of classical association schemes, wherein we fix an element of a fixed relation and count those that serve as intermediates of the other three fixed relations. This time, given XYZ in R1, the number of W such that replacing X with W yields a member of R1, Y with W yields a member of R3, and Z with W yields a member of R2 is 1. So, for example, let's take 1, 2, 2 in R1. The only W such that W22 is in R1, 1W2 is in R3, and 12W is W equal to 1. The fourth observation is that switching coordinates sends an Ri to another Rj. For example, if we switch the first two coordinates of R1, we just get R2. And the last observation is that the first four relations are the trivial relations, whose triples consist of elements that are not distinct. R0 is the diagonal relation. R1 consists of triples where the first coordinate is distinct from the latter two. R2 is where the second coordinate is distinct from the first and the third. And R3 is where the third coordinate is distinct from the first two. Here's the formal definition of an AST. It's a collection of ternary relations that partition the triple Cartesian product and that satisfies the following conditions. First, given a pair X and Y and the relation Ri, the number of Z such that XYZ is in Ri is independent of X and Y. We call this the third valency, and it's the analog of the usual valency from the classical case. Second is the analog of the symmetry condition, which tells us that given XYZ in RL, the number of W that serves as an intermediate of X, Y, and Z in Ri, Rj, and Rk is independent of XYZ. That is the number of W such that WYZ is in Ri, XWZ is in Rj, and XYW is in Rk depends only on I, J, K, and L. The third condition tells us that the set of ternary relations is closed under coordinate permutation. So swapping the coordinates of any relation will give us another relation. Finally, the last condition says that the first four relations must be the trivial relations, where R0 is the diagonal, R1 consists of the triples, where the first coordinate is different from the other two, and so on. Unlike in the classical case, where the valency is just a special case of the intersection numbers, the Ni3 are generally sums of intersection numbers. To look at ASTs as algebras, we jump from n by n matrices to n by n hypermatrices, along with an extension of the usual binary matrix product to ternary hypermatrix products. The multiplication now requires 3 inputs, but works in much the same way as the usual matrix multiplication. One index goes to the faces, one through the rows, and one through the columns. As in classical association schemes, the linear span of the adjacency hypermatrices is closed under ternary multiplication, and so forms a ternary algebra. Again, the multiplication is determined by the intersection numbers as structure constants. As an example, here's our AST from before, written as hypermatrices. As for an example of multiplication, let's consider a ternary product A4, A4, A3, which is equal to A3. Indeed, if we look at the entry at the first face, first row, and third column, the 113 entry, it's equal to the following summation. One index goes through the faces, one index goes through the rows, and the last goes through the columns. Like in the classical case, the product A4, A4, A3 is inside the span of the adjacency hypermatrices. Looking at the indices on the left-hand side and considering the coefficients of the bases on the right-hand side, we get P4430, P4431, and P4432, and P4434 are all 0, while P4433 is equal to 1. The following tells us that most of the interesting intersection numbers arise when the relations in question are all non-trivial. Indeed, the hypermatrices of the non-trivial relations form a subalgebra. Looking at this subalgebra is beneficial from a simplification standpoint. For unlike the algebras that arise from classical association schemes, not much is yet known about the ternary algebra structure from ASTs. Generally, these are not even associative or commutative, which one can check using the intersection numbers. We also don't have the usual notions of identities or inverses. As stated prior, not much is yet known about the structure of ASTs. We thought a good place to start would be to determine the sizes, third valencies, and intersection numbers of some families of ASTs. In this section, we see how ASTs arise from two transitive groups and how the parameters of the AST are related to the orbit of two-point stabilizers. Okay, so just as a brief review, if we have a group G acting on a set omega, the action is two transitive if and only if we can send any pair of distinct elements to any pair of distinct elements to an element of G. Or in other words, if A is not equal to B, X is not equal to Y, we have a member of G such that GA is X and GB is Y. First and foremost, the actions of two transitive groups induce ASTs. Indeed, the orbits of the action of the group on the Cartesian triple product forms an AST. For example, the AST that we've given before is obtained from the action of S3 on 1, 2, 3. As an aside, this is an interesting source of ASTs insofar as it's the direct analog of how transitive groups yield classical association schemes. The relationships between transitive groups and classical association schemes are deep, and what we're doing are hopefully the first steps to higher dimensional analogs of these relationships via ASTs and two transitive groups. Here's an example from the action of A gamma L 1,8 on the Galois field of 8 elements with primitive element A. The group itself isn't important right now. All we need is that it acts two-transitively. We can verify that all the conditions of an AST hold: the partitioning, the common outflow, the symmetry condition, the invariance under coordinate switching, and the presence of trivial relations. Some of the basic parameters of an AST are its size and its third valencies, or outflows. There's a close relationship between these and the 2-point stabilizers of the group. For example, consider the 2-point stabilizer of 0 and 1 in A gamma L 1,8. You can compute that it has 2 orbits, this and this. Notice that there are 2 non-trivial relations, one for each orbit. But if we look more closely, in the representatives of R4, whose first coordinates are 0 and 1, the third coordinates are given by this, and this, the members of one orbit. Similarly, the representatives in R5, whose first 2 coordinates are 0 and 1, have their third coordinates as the members of the other orbit. Stating this more explicitly, the number of non-trivial relations is the number of orbits, and the sizes of the orbits give the third valencies. Indeed, the situation we've observed holds in general. There's a bijection between the non-trivial relations and the orbits of any 2-point stabilizer. This can be seen from the fact that any non-trivial relation has a representative ABC whose first 2 coordinates are A and B. The other representatives of the relation whose first coordinates are A and B are then given by the members of the orbit of C under the 2-point stabilizer of A and B, establishing the bijection and telling us that the Ni3, the third valencies, or the outflows at AB are just the sizes of the orbits of the 2-point stabilizers. As a concrete example, we demonstrate how to obtain the sizes, third valencies, and intersection numbers of ASTs from the family of affine semilinear groups. We'll consider the one-dimensional case very closely, and then give the higher dimensional results more briefly later on. First, we define the affine semilinear group where Q is a prime power. It's the semi-direct product of the one-dimensional space over GFQ with its general linear group, and then again with the Galois group of the field. More concretely, an element of A gamma L1Q acts on the Galois field by a field automorphism, a non-zero scaling, and then a translation. For example, here's A gamma L1,8 acting on the field of 8 elements. Automorphism, scaling, translation. Here's the size and third valencies of the ASTs from A gamma L1,8. Notice that the 2-point stabilizer of 0 and 1 is just the Galois group. Thus, the orbits of a 2-point stabilizer consist of classes of Galois conjugates. In other words, an orbit consists of elements that can be taken to one another by a power of the Frobenius automorphism. In the current case, there are 2 orbits. From the prior theorem, this means that there are 2 non-trivial relations. Notice that their third valencies, which are the sizes of the above orbits, are the degrees of any representative of that orbit over the prime field. We'll show that these observations hold more generally in the next slide. First, let's determine the 2-point stabilizer of A gamma L 1p to the alpha. So any affine semilinear transformation looks like this. Yeah, okay. But the only affine semilinear transformation that preserves 0, those transformations can't have translations. Further, the only scaling that fixes 1 is the identity scaling. And so we get A is equal to 1. And that gives us this directly. In other words, the 2-point stabilizer is the Galois group. So the orbits are just the classes consisting of elements that can be taken to one another by raising them to a power of p. As for the sizes of these orbits, recall that over any splitting field, the number of Galois conjugates of A is just the number of distinct roots of its minimal polynomial. By separability, this is the degree of the minimal polynomial, and so is just the degree of the extension of ZP by A. Great, so we now have the orbits and their sizes, giving us the third valencies of our AST. However, to know the size of our AST, we have to know the number of non-trivial relations. To do this, we have to count the number of orbits, or in other words, the number of classes of Galois conjugates. We can do this through Burnside's orbit counting theorem. It says that the number of orbits is the sum of the sizes of the fixed points, all divided by the order of the group. In this case, we let the Galois group act on the field, and where there's a +2 here to account for the 0 and 1 that we removed. Finally, note that the automorphism, x mapping to xp to the beta, has order A over GCD, A beta, from the theory of cyclic groups, which, by Galois theory, implies that the fixed field has this order. And that's precisely what we wanted to prove. So we now have the information we need for the sizes and outflows of the AST from A gamma L 1p to the alpha. We have these are the non-trivial relations, one for each class of Galois conjugates, and the outflow of such a relation is the degree of element in the corresponding class. Let's now provide a sample computation of intersection numbers in A gamma L 1/8, whose method also shows us how the general situation is handled. We'll show that A4, A4, A4 is A4 plus A5. Recall that the hypermatrices of the non-trivial relations form a ternary subalgebra. So A4, A4, A4 is the sum of P4, 4, 4, 4, A4 and P4, 4, 4, 5, A5. Hence, we need to show that both of these intersection numbers are equal to 1. Let's start with P4, 4, 4, 5, taking 0, 1a cube as our representative of the top index R5. The intersection number is the number of z such that z1a cube, 0za cube, and 01z all belong to the lower index R4. Let's just look at the second condition here. It tells us that there's an affine semilinear transformation sending 0, 1a to 0za cube. Such a semilinear transformation sends 0 to 0, so there can't be a translation. Since it scales 1 to z, that means the scaling factor has to be equal to z. Simplifying, we see that z times a Galois conjugate of a must be equal to a cubed. If we plug in the powers of the Frobenius automorphism and then solve the resulting equations, we get the following candidates for z. The other candidates for z can be obtained in a similar fashion through the first and the third conditions. Take particular notice that our desired z can be obtained by considering a system of 3 equations, these ones in blue over here. Okay, now we have that the only z that satisfies all the conditions above is A. So P4445 is 1. As I said before, we can also combine the equations above so that P4445 can also be obtained by counting the number of conjugates of A that satisfies the following. The intersection number, P4444, can similarly be obtained. Great, we verified that A4, A4, A4 is A4 plus A5. However, a more convenient form for generalization can be accomplished by writing A4 as AA and A5 as AA cubed. Briefly, it says that the intersection number PA to the I associated with AA to the I is the number of conjugates of orange such that conjugates of red and blue exist such that these expressions are equal to A to the I. This extends to the more general formula for ASTs from A gamma L 1P to the alpha. Again, it says that the intersection number PL associated with AL is the number of conjugates of C such that conjugates of A and of B exist such that these expressions are equal to L. Let's now increase the dimension by considering A gamma L to P to the alpha. We'll see that it behaves mostly like the one-dimensional case, just with one additional orbit. This time, the vector space upon which we act is two-dimensional. Instead of non-zero scalars, we work with invertible linear transformations, and now translations are with two-dimensional vectors. The Galois group acts on the vectors component-wise. As before, we want the size, outflows, intersection numbers from the AST from this group. For that, we'll first need the orbits of a two-point stabilizer. The two-point stabilizer of 0, 0, and 1, 0 consists of the transformations with the form below. To see this, note that to fix 0, 0, there can't be a translation. And to fix 1, 0, the first column of A has to be 1, 0. And that's the only restriction. Let's now compute the orbits of a two-point stabilizer. Given a vector A0, applying the transformations in the stabilizer yields the following orbit. These are the vectors with second component 0 and first component Galois conjugates of A. If we ignore the second coordinate, it's just 0, it looks like the situation from the one-dimensional case. In particular, the size of such an orbit is the degree of A over the prime field. Thus, the case where the second coordinate is 0 behaves just like the one-dimensional situation. But what about the orbits of those whose second components are not 0? It turns out these all belong to a single orbit. Indeed, applying the transformations in the stabilizer means that we get all vectors that can occur as second columns of matrices in this form. The only restriction is the invertibility of the matrix, or in other words, that the column CD is linearly independent from 1, 0. And there are P to the alpha squared minus P to the alpha such vectors. Using the relationships between the orbits and the AST, we see that there are these many relations of the given form, each with outflow given by the degree of A. There's just one more relation than the one-dimensional case, given by R star, corresponding to the vectors independent from 1, 0, and whose outflow is the number of such vectors. The intersection numbers behave much like the one-dimensional case when the relations involved are all of the form A0. Or in other words, we have three matrices of the form AA, AB, AC. However, there are additional results which corresponds to multiplication that involves the relation R star. A star, A star, A star. We're not going to fully illustrate the result. However, to make clear just how similar the situation is to the one-dimensional case, consider the following. Here we're working in A gamma L28, and we want to determine Z1, Z2 such that this triple is in the orbit of this triple. This is the same as asserting the existence of a matrix, a translation, and an automorphism that sends this one to this one. Since 0, 0 is sent to itself, there can't be a translation. Since 1, 0 is sent to Z1, Z2, the first column of A has to be Z1, Z2. Finally, multiplying A to the third column gives us the following equality. And considering the third coordinate, and then ranging over the automorphisms, we see that Z1, Z2 has to be one of the three options. Ignoring the second coordinate, it's just 0. This is just like the one-dimensional case. These results that we've said on the orbits, their sizes, and their intersection numbers also carry over almost verbatim for dimensions greater than 2. The proofs and methods also carry over almost verbatim. In this section, we summarize our work. We were motivated to study ASTs because of the ubiquity of its lower dimensional cousin, the classical association schemes. We briefly reviewed classical association schemes to motivate ASTs. We saw that the resulting structures from ASTs have yet to be fully studied. And so we were motivated to consider basic parameters of some families of ASTs, their sizes, their third valencies or outflows, and their intersection numbers. We focused on the families of ASTs from two transitive groups and how the orbits of two-point stabilizers and their sizes yield the non-trivial relations and third valencies of their corresponding ASTs. In particular, we looked closely at the ASTs from the affine semilinear group. Over dimension 1, the orbits are just the Galois conjugacy classes, whose sizes are the degrees of any of its representatives. We also saw how to obtain the intersection numbers. Finally, we extended these results to the two-dimensional case, and this also mirrors the higher dimensional cases. As a bit of an aside, here are the other groups that I've been working on for my dissertation. Although we can obtain the two-point stabilizers, the orbits, and the sizes of all of these, I was unfortunately unable to determine the intersection numbers for the groups in items 4, 5, and 6. So this remains open. I had trouble because of their unwieldy representations, but maybe someone has a better idea of handling these groups. Some of these act on Steiner systems or other geometric objects. So maybe the representation is easier to use when they act on those systems. Anyway, here are some other possibilities for work. We could consider other two transitive subgroups of A gamma L. We could also look at small examples of ASTs, which we've done. It's in Matemias now. We looked at some small examples of ASTs and saw that some of these can be obtained from two transitive group actions. There's a lot more that could be said if we could improve the algorithm or had a better computer. So there's one direction again. Another one is by Messner and Bhattacharya. I think it was 1994. They looked at analogs of identities and inverses of the algebras from ASTs. We might want to look at these for the ASTs from the two transitive groups and how to compute them. They have examples of this, but I think they didn't handle all of the two transitive groups. So there's something to work on there. It would also be nice to learn more about the structure of ASTs as hypermatrix algebras. There's a paper by Lister on structure theories for when the hypermatrix algebra is associative. Or in other words, there's a ternary algebra theory for associative ternary algebras, including substructures, quotients, modules, even Wedderburn-Artin theory. But we haven't really found an example yet where the subalgebra from an AST is associative, except for some trivial cases. It would be nice to have a basic theory of quotients, products, substructures, and so on, even without associativity, or even just for ASTs specifically, whether algebraic or combinatorial. Another thing to consider might be to work on the spectral theory of hypermatrices. There's some work by Nang on this, which gives a sort of analog for spectral theory for hypermatrices, and even a 2021 paper on as an analog for the general linear group, but for hypermatrices. I mentioned this because in the classical commutative association scheme case, the adjacency matrices are normal and commute, so they are simultaneously unitarily diagonalizable. The projections to the simultaneous eigenspaces in the forms of matrices actually form a basis of minimal idempotence of the adjacency algebra, in particular showing that the algebra is semi-simple, and so is a direct product of fields, and where we can know the one-dimensional representations quite explicitly. It would be nice if we could find some analogs for commutative ASTs. We have found some examples of subalgebras of ASTs that are commutative, but again, we don't really have the structured theory to look at them more closely. And that's it. These are just the references. Thank you very much for having me and listening to my talk.
Okay. Thank you very much, Mr. Briones, for that nice talk. Could we all give Mr. Briones a round of virtual applause? Okay, thank you. The floor is now open for questions. So if there are questions or comments from the audience, or maybe feedback for the perspectives that was mentioned earlier. Dr. Lope?
Hello, good afternoon. Magtatanong lang, anong computer algebra system ang ginagamit mo? Na-mention mo na may parang gumagamit kayo ng computer, no, to simplify, kasi medyo masalimuot na nga yung my expressions. Ano yung CAS na ginagamit mo?
Ang ginagamit ko po, sir, ay GAP.
Okay. And what particular aspect ng numerics ang nagpapahirap? Also, kasi na-mention mo na you need better computational power ba yun? Or
Yes,
do you
po.
just need better or more memory? Which particular yung kailangan mo?
Yung ginawa po kasi namin, Doc, for the classification is that essentially, generate niya yung mga ASTs over small vertices. Generate niya isa-isa through partitions ng omega cross omega cross omega. So tinitignan niya lahat essentially ng mga partitions. Chine-check niya doon which ones yung ASTs, and then chine-check niya yung uniqueness nila up to isomorphism. So it's somewhat a brute force algorithm. So yung kanyang growth when it comes to computation is very large kasi we're working with omega cross omega cross omega. Yung tinutukoy ko pong improvements on the algorithm, yung hindi po yung computational side. Of course, if we had more computational power in memory or in processing speed, we could compute some more examples. But what I'm referring to as improvements to the algorithm was in the classical case, in the works of Hanaki and so on, and etc., etc. For classical association schemes, may mga relations po between the intersection numbers and other parameters that can be restricted, so they don't have to check all of the partitions of omega cross omega cross omega. But unfortunately, since in ASTs, we don't know yet much about the structure, wala pang mga corresponding inequalities like those that I could find, that I could use to improve the algorithm. So at the moment, it's just a fairly brute force attack. I hope that helped.
Yeah, thank you. I suppose ganun nga. I mean, by doing concrete examples, maybe you find patterns, and then that's where you try to prove whatever relationships that you observe, no. But yun nga, meron tayong computational research laboratory sa math. I am not just sure. I think GAP runs on Mac OS, right? Hindi naman po namimili si GAP.
Yes, I think yes, sir.
So yun, maybe you can explore that possibility. And kung talagang kulang pa rin tayo sa math, there's also the computational research center sa College of Science, which you can also tap. Yun lang. Thank you.
Thank you, Doc.
Thank you, Sir Ernie. Maybe a follow-up on that. So Dom, yung ginawa mong computations, that was for the specific K at saka yung power ng prime. Ano? May specific value ka na hindi siya yung tipong magagawa mo siya for a general P na i-input lang yung P na yan na prime or so hindi pa na for a specific.
Yung for
so yung mga pinakita mo kaninang examples on yung mga pinakita mong examples on finding the yung parameters, yung intersection numbers, etc. So those are for the specific values na nung sa do sa A gamma L.
For A gamma L. Apo yung intersection numbers.
Yes,
although binigay ko pong specific example yung for P to the alpha is a power of 2. They work for any prime power. Okay na po sila.
So yung algorithm mong ginawa is applicable naman siya for ano?
Yes, they work for any prime power, yeah. For any family.
I see. Yeah. So in relation to Sir Ernie's question, kasi baka pwede siyang ma-run general and it will need some additional computing power, then maganda suggestion. So
thank you.
Okay, thank you. Do we have any other question? Questions? Okay, so kung wala na po tayong questions, let us again thank Mr. Briones for giving us this nice talk. Thank you. So applause po tayo ulit kay Mr. Briones. So thank you very much, and I would like to thank everyone for attending and listening. So our next webinar will be 2 weeks from now. I think that is on 21. March 21. So for now, the schedule is that we'll be hearing a speaker from the Matrix Analysis and Linear Algebra Group. Okay, so again, thank you, Mr. Briones. Thank you to all those who attended. Okay, so see you in 2 weeks. Goodbye. Hey, Sir Joey.
Salamat, Gino. Sa mga nandiyan pa, yung defense ni Dom sa March 25 yata. So,
yes.
find
ito po ay colloquium, so defense niya ng March 20. Good luck, Dom, sa defense.
Okay. Congrats, Dom.
Sige po.
Thank you, sir.
Bye.
Kita ulit tayo sa 25.
Afternoon.
Apo.
Okay.